Welcome to this tutorial about thermochemical equations. In this tutorial I'm going to be introducing what a thermochemical equation is, and also we're going to have a look at how to use thermochemical equations to find different quantities. So performing calculations using thermochemical equations. To begin with, a thermochemical equation is essentially an equation that shows the enthalpy of the reaction. Okay, so an example of that. Now, in your data book, you're provided with these fuels, and I'm just going to use, say, ethane. Okay, so we can see ethane is C2H6, and I'm going to write a thermochemical equation. Sorry, I'm getting rid of that too. And that's meant to be a 6. Plus oxygen gives us carbon dioxide and water. So now we have to balance the carbons. So we have 2 carbons on the left hand side, and so we need 2 carbons here. Next we're going to have a look at our hydrogens. So we have 6 hydrogens on the left hand side and only 2 hydrogens on the right hand side. So we need 3 in front of this hydrogen. And so now we've got 3 times 2, so 6 hydrogens. And finally we look at our oxygen balance. So oxygens, there's only 2 there, and here there are 2 times 2, so 4, plus another 3 oxygens. So there's actually 7 of them. So what we need to do is we need to make sure we need to multiply the side with a lower number of oxygens. If we just set it up here, so we know on the left hand side we have 2 oxygens, we need to multiply this 2 by a certain number, a certain unknown number, and get it to be equal to 7. So we're looking for what x is equal to. So x is equal to 7 over 2, which can also be written as 3.5. So we know we need 3.5 oxygens. Now, it's not a good idea to have 3.5 oxygens in your chemical equation. So what we're going to do to that equation that we've balanced is we need to times it by 2. We're timesing by 2 to get rid of the 0.5. So that means we've got 2 C2H6 plus 7 oxygens give us 4 carbon dioxides plus 6 waters. Now we then write because we're asked to write a thermochemical equation, we write delta H, and we're looking for delta H of ethane. Now ethane is here, and the value I'm actually going to work with is this one here, because kilojoules per mole is usually regarded as the safe bet when you're writing out your thermochemical equation. Remembering though that this here is listed per, it's kilojoules per 1 mole. In this chemical equation we actually have 2 mole of the fuel. So we're going to have to take the enthalpy is going to be minus 1560 times by 2. So that's going to give us minus 3120 kilojoules per mole. Okay, because we have double the amount of ethane. So the table, this table here that you're provided from VCA, it's always per 1 mole. So in this situation our value changed because it's 2 mole. So the final way you write it Okay, or express your answer would be just writing it negative 3120 kilojoules per mole, making sure that you have the units and you also have the sign. So this table didn't give you the sign of the heat of combustions, but they're all negative values since they're all combustion, and that means that the enthalpy is negative because it's an exothermic reaction. Okay, so that's an example of a thermochemical equation. Another example of a thermochemical equation is, say, burning of glucose. Plus 6 oxygens give us 6 carbon dioxides and 6 waters. So I just remember this balance, but you can work it out if you need to. Delta H is equal to negative 2,800 kilojoules per mole. Okay, so that's another example of an thermochemical equations. Okay, so we're going to be using this table in a few of these questions to perform our calculations. So I've written up a few examples here, but before we look at the examples, we have to discuss what you're finding in thermochemical calculations. So thermochemical equations can be used to calculate various quantities, including how much energy a reaction releases. So say you have, the volume of of ethanol given, or you happen to have the mass of glucose. You can use that and the enthalpy of the reaction to calculate how much energy that glucose releases when it's burnt. So that might be significant in knowing what will happen in a combustion reaction when you start burning something, how much energy is actually released. It can be quite an important value to know, so that to avoid potential melting of your equipment, etc. How much mass of a reactant is needed to produce an amount of heat. So in these kinds of cases, you know the energy that you want to attain, but you don't know how much of the material is required. So we will look at that kind of style of question in the next examples. But also it's important to consider the unit of enthalpy that's provided. So I would always check what unit you're given, because the unit actually dictates how the calculations will take place and what you're working with. So if you're very careful with a unit, you can use it to guide you through the question. I'll show you what I mean in a moment. So let's have a look at this example. Example 1. So this amount of glucose, so we have 3.45 grams of glucose was oxidized completely, and the heat of combustion is this amount. So heat of combustion is an enthalpy, delta HC. You don't need the C there. Okay, when you're writing the thermochemical equation, we had it before, C6H12O6, usually sugar is a solid, plus 6 oxygens, they're in gaseous state, gives carbon dioxide, gaseous, and water. Usually it's also in gaseous if it's combustion, because water turns into a gas, because the temperature is usually over 100 degrees, and delta H is minus 2,800 kilojoules per mole. Okay, so that's our thermochemical equation written out. Making sure that you have the correct states, and all you have to do is just insert the enthalpy at the end. Now question B asks us to calculate the amount of energy released when this amount of glucose is completely oxidized. Okay, so what we know from our above reaction is we know the mass of our glucose. Mass of glucose, C6H12O6, is equal to 3.45 grams. Okay, now if we look at our enthalpy states that it's kilojoules per mole in this reaction. Okay, so it's no good working with masses of glucose. We want to work out the molar mass of glucose. C6H12O6 equals to the molar mass is equal to 180 gram per mole, and then you can use that to calculate the mole of glucose. So I'm just going to try to get my calculator out. Okay, so we're just going to use this. We know we have 3.45 divided by 180. Okay, so we can see our answer there. Now, so that gives us our mole. Mole of glucose. It's mass over molar mass. So that was 0.019166. Okay. Mole. Okay, so that's our mole of glucose. Now what we need to do with that is we have to work out, we're asked to find the energy released. So I'm just going to make some more space. Okay. So what is a good idea in this case? This is when we're setting up a table. I like to set up a table. It makes it less confusing. So I know that we have, from our enthalpy, we are comparing how much energy is released per every mole. Okay, every 1 mole. So we're going to set up a table with the mole on one side of the table compared to the energy on the other side of the table. So what we're going to do is we know that from our enthalpy there is 2,800 kilojoules of energy. This is in kilojoules, and that's mole. So every 1 mole of substance of this particular glucose releases 2,800 kilojoules of energy. Now I haven't put in a negative because it's not relevant. We know that energy is being released, and what that negative implies is that energy is being released. So if we already know that, we don't have to include it in our calculations. So then the other thing that we know is we know how much mole of glucose we are burning. So we will use that value, 0.019166 mole, and we don't know the amount of energy that's released. Now what we can use this box for, or this table for, is we can use it for a cross multiplication. The proportions will be the same as long as you align mole in one column and energy in another column, and you make, you can't just mix this up and put energy on this side and then another energy value on the other side. It's not going to work. But essentially what we're doing here is we're finding, we're multiplying 1 by the x, so 1 times by x, which is just x, equals to 2,800 times by 0.019166 mole. And by doing so, we are actually finding the unknown energy there. So we're going to take that value that we just had before, and we're going to times that by 2,800. We get 56.767. Okay. 56.6666. So on. And that's actually the kilojoule value. Okay, so that's in kilojoules. So essentially, now we have to look at the significant figures. So with significant figures, they're important to consider in the question. They will dictate the accuracy of your answer. So in this case, we have 3 significant figures, okay, in the 3.45. So what we do to our answer, if we look here, is we will count up to 3 values and then cut it off after. So this 6 here is going to increase the 6 there by 1 unit up. Okay, so it's going to become x equals to 56.7 kilojoules. So the answer is therefore 56.7 kilojoules of energy is released when 3.45 grams of sugar is combusted. And so whenever you have some form of units, you can use this table to essentially set up your calculation. We'll be using this quite a few times, so hopefully that will give you enough practice. But let's have a look at question C. Okay, question C is asking you how much glucose in grams is required if 50 milligrams of energy is needed. Okay, so alright, now so our energy is equal to 50 megajoules. So 50 megajoules is 50 times 10 to the 6 joules. Okay, or it can be considered as 50,000 kilojoules. You would take the joules and divide it by 1,000. Okay, and then you would get 50,000. So that's how many kilojoules you have. Now, going back to our table, it's quite important to set this up again. This time, how much glucose in grams? So we still are working with mole at the beginning, because we have our enthalpy is in kilojoules per mole. So mole, and this is energy. So for every 1 mole, 2,800 kilojoules is released. And for this scenario, we don't know how much mole of glucose is required, but we do know that 50,000 kilojoules of energy is required. Now, you can't put 50 into there, because megajoules is not the same as kilojoules. Okay, so you must make sure that it's the same energy unit as well. So now we're going to do the cross multiplication again. So 1 times by 50,000, and this times by this. So I'm just going to set it up for us. 2,800 times by x equals to 1 times by 50,000. So x is equal to 50,000 divided by 2,800. And that will give us our mole. So let me just calculate that. Clear 50,000. Okay. Divided by 2,800. So 17.857. 17.857. And that's in mole. Okay, so we know this value now. We know what x is. Now, the next thing we have to do is we need to convert the mole back into a gram value. So the mass of glucose this time we take the mole and we times it by the molar mass, okay, which is the 17.857, and you multiply it by the molar mass of glucose, which is 180 gram per mole. Okay, so we're going to do that now, times 180. So 3,214. Point 2857. 2857, and this is in mole. Sorry, that's in grams. My mistake. So yes, we've got grams here. So that's the value in grams of glucose. Now, if you check your significant figures again, in this case, the significant figures, there are only 2 significant figures. If you wanted to find this answer in the correct amount of significant figures, the first thing you need to do is turn it into scientific notation. So 3.124287 times 10 to the power of 3 grams. And then 2 significant figures, so you count the 3 and the 2 that go in front. This 1 will not boost the 2 up, so basically your answer is 3.2 times 10 to the 3 grams of glucose. That's what you would do correct to the significant figures that the question has given. Okay, so let's have a look at question 2 now. So we know that ethanol was combusted to obtain, sorry, this is, I think, yep, it is question 2. Ethanol was combusted to obtain 40 kilojoules per every hour. Write the thermochemical equation for ethanol. So I'm just going to get a bit more space. So in this question, we need to we write ethanol, which is this, plus oxygen gives us carbon dioxide and water. Now, doing the balancing this chemical reaction might be a bit tricky, so I'm just going to get more space. We'll start off, I suppose, with whoops, sorry. Just hard to find my cursor. Okay, so we start with the carbons. So there are 2 carbons on this side, and there is only 1 carbon on this side. So I'm going to write 2 in front of there. So that makes the carbon balances correct. The next one is the hydrogens. So I have 5 plus 1 hydrogen there, so 6. And I only have 2 hydrogens on this side, so I need to times it by 3 to get the correct number of hydrogens. And finally my oxygen. I have 2 oxygens on this left hand side, and on the right hand side there are 4, 2 times 2, plus 3, so that's 7. So once again we need to balance the oxygens, so 2 times by an unknown number, that gives us 7, and if we transpose this equation we get x as 3.5, so there's 3.5 oxygens. And I'm just once again going to get rid of all of this, including the atoms, and I need to times, or I need to multiply this entire equation by 2, because I can't keep my equation with half of a molecule. It just doesn't make sense to have half of a molecule. So C2H5OH, usually it's a liquid state, plus 7 oxygens in a gaseous phase gives us 4 carbon dioxides and 6 waters, and both of those are in gaseous phase. Now we're not given any enthalpy, but that's okay because we know from our table, from our data book, we can find the enthalpy of ethanol. Okay, and in this case we could choose to express it in kilojoules per gram, or we could choose to express it in kilojoules per mole. I'm going to stick with kilojoules per mole. Now remember that that's considered as 1 per 1 mole, so delta H of ethanol is minus this kilojoules per mole, but in our chemical reaction there we have actually 2 moles. So we need to take delta H and we need to times it by 2. Okay, so the delta H when we times it by 2, so this, that would be 7. So negative 2,720 kilojoules per mole. So that's the value that we have to write here. If there was 3 in front of your ethanol, you would have to multiply that delta H by 3. Okay, so the delta H needs to be adjusted based on the number in front of your fuel, or whichever substance you're dealing with. Okay, so question B states, calculate the mass of ethanol required in 1 day. So 1 day contains 24 hours. From our information at the top there, ethanol is combusted to obtain 40 kilojoules per every 1 hour. So what we're going to do at the start is we have got, let's just consider for 1 hour. Consider how much ethanol is used in 1 hour. In 1 hour. So if we consider that, we know that the energy is the energy and time. There's 40 kilojoules of energy produced every hour. So energy equals to 40 kilojoules. And we want to find how much mass of ethanol is needed. So what we need to do is we first need to probably work out how much ethanol is required per every hour. So if we set up our table once again, with our mole, and in this case our energy, for every 1 mole of ethanol, 2,720 kilojoules of energy are required. So we don't know how much mole is produced, how much mole is required to produce 40 kilojoules of energy. But we can work it out because we know now that cross multiplication works very well in this situation. Okay, so to cross multiply, we just go 2,720 times by x equals to 1 times by 40, so it's just 40. So x equals to 40 divided by this, which we can use again our calculator for that. 40 divided by 2,720. Okay. So 0.0147. Mole. Okay, so that's the mole of ethanol. What we can then do is we can get back to the mass of ethanol. Now we know in this case that the mole of ethanol is equal to 0.0147 mole, and the molar mass of ethanol, well, that can be calculated by calculating what the molar mass is of the substance. So we have 24 plus 16 plus 6 from our hydrogen value there. Yeah. So in that case, that gives us 46. Okay, so our molar mass is 46 gram per mole. And then we can work out the mass. So I'll write mass of ethanol. So we multiply the mole by the molar mass. So times by 46.676. Notice how I use my accurate answer. I carry my answer on the calculator. I'm not deleting it yet. So that's the mass of ethanol that's produced in 1 hour, and I keep doing this where I'm placing in the incorrect unit. That's meant to be grams. Okay, so now we're taking this amount. This is per 1 hour. We need to get it in 1 day. So we have to times it by 24 hours. So the mass in 1 day, ethanol in 1 day, is equal to the value we have there times by 24. So we're going to take that value and times it by 24. So 16.235. 16.235. Just need to find it again. 16.235 grams. And then we look at the significant figures, and we find that we just have 2 significant figures to deal with. So it's approximately 16 grams. Okay? So that's how much ethanol is used in 1 day. Alright, finally, let's have a look at question 3. So question 3 says, octane has a density of 700 kilojoules per meter cubed. And these units, meter cubed is found in your data book. We will have a look at how to use this in a second. So this is the density of ethanol, octane. If a car uses 12 liters of octane, calculate the amount of energy released by the combustion of this octane. So octane, remember, is C8H18. We want to start off with writing a thermochemical equation for it. So we're going to set it up. Okay, we have the number of carbons on this side is 8, the number of carbons on this side is only 1, so we need to times this by 8. Then, so the carbons are now balanced, the hydrogens, there are 18 of them, and only 2 of them there, so we need to times by 9. Now the hydrogens are balanced. And finally we're left with the oxygens, and the oxygens are probably going to be the most annoying to balance, so I'm just going to write this out. So oxygen is 2 on that side, and there are 2 times by 8, so 16 oxygens on that side, and plus 9 oxygens from the water, and that gives us 25 oxygens. So once again we need to balance the left hand side with the right hand side, so 2 times some amount is equal to 25, and we want to find what the factor x is. So x is 25 over 2, which is also 12.5. So we need 12.5 oxygen molecules to turn both sides into balance, so to have 25 on both sides. So once again we're going to have to multiply this entire equation by 2. And once again, whatever the delta H of the reaction is, we're going to have to take that value and times it by 2. Okay, because we have double the amount of octane. And I'll just get the value of delta H for octane. So we can see that it's 5,460. So that's minus, and we're doubling it. So our thermochemical equation is going to be 2C8H18 liquid plus 25 oxygens in the gaseous phase, create 16 carbon dioxide plus 18 water molecules in the gaseous phase. And the delta H of this reaction is minus 10,920 kilojoules per mole. Okay, so in this case we well, we can write our thermochemical equation, but it's not a requirement. I just kind of showed you how to do it, but in this case, if you wanted a shortcut, you would just use the value from the table. Okay, so you just, if you used 5,460, you would be fine as well. So I'll show you the two methods of working this out. So first of all, you know the volume of octane that you have, but you don't know because the density is given to you. You don't know how much mass of octane you're dealing with. Okay, because remember the density, it compares the mass with the volume. The volume is in units of, in this case, meters cubed. What I'm going to change it into, I'll just write it here. So 1 meter cubed is equal to 1,000 liters. Okay, so what I will do is I'll say that 700, and this is in kilograms. I don't leave my volume in liters. I prefer working with liters. 700 kilograms of octane takes up a volume of 1 meter cubed. So 700 kilograms requires 1 meter cubed. Okay, so instead of writing 1 meter cubed, I'm going to convert my meter cubed into liters. So 1,000 liters. I don't know how much mass of octane is in 12 liters. Okay, so that's why I left it as X in 12 liters. So what we're going to do, once again, we are going to, this is a cross multiplication situation. So you multiply that side, multiply that side. So you get 1,000 times by X equals to 700 times by 12. Okay, so we'll work that out. 700 times by 12 divided by 1,000. 8.4. So X is equal to 8.4 in this case. And that's in kilograms. So 8.4 kilograms is needed of octane in this situation. Now the question asks not how much kilograms of octane is required, it's how much energy. Does 12 liters release? So once again we can look at our thermochemical equation where we're using the mole and we're comparing it to our energy. And we know that for every 2 mole of octane, we have 10,920 kilojoules of energy. And we know that in this case we have the mass of octane is 8,400 grams. You can calculate the molar mass of octane by just looking at the formula. So you have 8 carbons. So 8 times by 12 plus 18 hydrogens. It's 114. So that's the molar mass of octane, 114 grams per mole. And then from that we can work out the mole of octane. So 8,400 divided by 1,114. And that's equal to so 8,400 divided by 114. 73.68 mole. So we then put that information into here. So 73.68 mole gives us a certain amount of energy. Okay, so once again we have to, whoops, excuse that for a sec. Okay, so we have to multiply this through. So we've got 2 times by x equals to 73.68 times by 10,920. So x is divided, that whole value needs to be divided by 2. So we times it by 10,920 and divide the whole thing by 2. So sorry, 2315.789. Okay, and that's the value in kilojoules. So finally, what we can do is, that's quite a large value in kilojoules. I do prefer to change it into a nicer, more condensed format. In this case, I'm going to move the decimal place. I'm going to get it into megajoules instead. So I'm going to turn this into megajoules. And to do that, to go from kilojoules to megajoules, we divide it by 1,000. So that decimal point there, it's carried by 3 decimal places to the left, and the answer is 402.31 megajoules. And then we will look at significant figures. So there were only 2 significant figures there. So we have to, in that case, make this 4.0 times 10 to the 2 megajoules. So I've turned it into scientific notation, and then I've gotten rid of the 2 because that's not significant. And so this is it to 2 sig figs. So that's how much energy 12 liters will release. So I did mention that we could do this in a slightly different way. And first of all, where we had our thermochemical equation written out, we didn't even need our thermochemical equation. Our table would have been fine. Here, where is our calculation? Here, our table would have been fine even if we had just 1 mole of, if we knew 1 mole of, in this case, octane, how much energy it produces, so 5,490. That the proportion would still be the same. Okay, so you could use the value directly given by the table. So, sorry, it was 5,460. And also, instead of using, because we were converting into mole in this situation, we could have kept the whole question into as kilojoules per gram. It would have been easier to deal with than kilojoules per mole, because mole had to be converted quite a few times. We had to do extra calculations. So see where we had the mass of, we already had the mass of octane given to us there. We could have used the enthalpy kilojoule per gram instead of kilojoule per mole, and that would have given us the same answer. Regardless of how we did it, the answer is correct in this situation. We have found You know, we have compared mole to energy instead of grams to energy. So there's a few ways of going about these questions. Later on, you know, it may be more efficient for you to actually use kilojoules per gram. And the way you'd know when this is appropriate is you'd look at the units that you're dealing with. So in this case, it's mass.